Hi, in this video I want to talk about angular momentum and the conservation of angular momentum. These are both keyed to Young and Freedman's University Physics, Chapter 10, Sections 5 and 6. So without further ado, do you remember linear momentum from Chapter 8 or from whatever textbook you were using earlier? Linear momentum, you might remember, is that it's denoted usually by p, and it's a vector, so it has a direction. And so linear momentum is basically mass times velocity. And again, velocity is a vector moving in a certain direction. So P equals mv is one way to express linear momentum. That is, momentum of an object with a certain mass moving in a certain direction with a certain velocity. So that's linear momentum. For angular momentum, it's very analogous. So we use often a capital L for angular momentum. And it is the cross product of the radius from whatever, if we're talking about angular momentum, we're talking about something, the momentum of something that's rotating, or that's spinning, or that's moving in a more circular direction. And there's your P for the momentum of a point. Let's say I've got a little sling, I'm going to kill a giant. I've got a rock in a sling, and I'm swinging it around. So that rock has a certain momentum, as it goes around that circle. So if you take that momentum of the rock at a certain point and the radius from wherever the center is to that rock and do the cross product, there's a video in YouTube land that I've done on getting cross products from Chapter 1 of Young and Freedman's Physics, 110 I think it is. So this is going to be a three-dimensional cross product using the right-hand rule. If it's spinning this way, then you're going to use your right hand. It may look opposite in the video, but in my world, it's a right hand. And then you curl your fingers in the direction of the rotation, and the z vector is whichever way your thumb's pointing. So you take the cross product of the momentum from whatever center point or origin point. Now you can conceive of the point from which it's rotating differently, use a different origin, and then it's going to have you're going to conceive of it as having a different momentum. So anyway, my point is that you can see that angular momentum is simply linear momentum with a radius of sort, an r, thrown in there from the point of origin to wherever the point is that is rotating or spinning at an angle, so to speak. So it's very analogous to linear momentum. Similarly, there was another way to conceive of linear momentum. In fact, this is the way that Newton himself conceived of force in the first place for his second law. So the sum of all the forces in a body basically amount to the change in momentum per instantaneous time, dp dt. So the instantaneous rate of change of momentum per time is basically the force, the net or the sum of the forces. That's something we learned, again, way back in, I think it was Chapter 8. So a second item here is that momentum, whether it be linear momentum or angular momentum, is conserved. That is, if the vector sum of external forces on a body is 0, then the total momentum for that body is going to be constant. It's not going to change. This is one of those great conservation laws of physics, that momentum is conserved. There's no loss of momentum. Similarly with angles, as we are saying in this video, that for angular momentum, it is conserved as well. There's no loss of angular momentum if there are no external torques on a body. So what we're going to find is, just as for linear momentum, the sum of the forces is the instantaneous rate of change of momentum per time, so the sum of the torques on a rotating body is the instantaneous rate of change of angular momentum per time. So there is also this conservation law for angular momentum. If the net external torque is 0, then the total angular momentum for a body is going to be conserved. Okay, so that's the majority of what you should get out of the two sections that we're looking at here today. But let's look at some diagrams to make it a little more complicated. We can't let it be too easy, so let's get into the weeds here. So here we have a point. I put it in a random XY framework, and let's say we have a mass, a point mass that's moving in a certain direction. Then momentum, for linear momentum, P equals mv. Okay, review from Chapter 8. Now, maybe I should have broken this down into sections, but basically let's say we have that same point mass moving in a certain direction. But let's say that it's rotating around an origin O. And so there you can see R. R is that distance from the origin to the point mass where it is. And so if we want to figure out the angular momentum, there are a couple of ways to do it. So for example, if we take the line, the direction that the point mass is moving in, and we extend it back and then make a right angle with the origin to make a little right triangle, then this line here is the same as the lever arm that we saw for torque at the beginning of this chapter. And so that small l, that's supposed to be a small l right here, that's supposed to be a small l, using some basic trig. So if the angle between, say, the line from the origin on out through the point, if the angle between that line and the direction in which the point is moving, if we call that phi, these opposite angles are going to be the same. So phi here, if I take the sine of phi and multiply it by r, which is the hypotenuse, then I have r sine of phi is going to tell me what the length is of this lever arm here. So here we have mvl. So this is mv, remember, P equals mv. So the momentum of that particle is mv, and if I multiply r times the sine of phi, that gives me the lever arm. So if I multiply this by the lever arm, that's going to give me the angular momentum for that point mass. Okay? The other way to conceive it is if I draw a perpendicular to this r, and then make a right triangle with the momentum, then this angle here is going to be phi, because these are opposite adjacent angles here, or not adjacent, but opposite angles, and so they're going to be equal in measure. So here again, if I take multiply the mv times the sine of phi, I'm going to get this length here, and if I multiply this length here times r, then I'm going to get mv sine of phi times r equals, again, the same thing, L. So these are different ways at the bottom here of conceptualizing how I can get the angular momentum for a particle moving in a rotating dimension around an origin. Two ways to do it. If I can get this L, this lever arm down here, and multiply it by mv, I can get it. Or if I multiply this perpendicular here times r, I can get it. So the angular momentum is going to be mv times the sine of that angle times r. That's not a dot product. That's just a times. Or mv times the lever arm L, and that both of them are giving me the cross product of r with p, or r with mv, same thing. And of course, that cross product, I'm going to use my right-hand rule to figure out what direction it's going at. A little complicated, but just memorize the formulas until you understand it. So here again, to go over the formula, just to kind of summarize what we've just said, the angular momentum L is the cross product of r from whatever point of origin to the point mass that has a certain momentum. P equals mv, so to say that it's the cross product of r with p is the same thing as to say it's the cross product of r with mv. You'll remember that to find the cross product of something, you multiply it by the sine of the angle, and so that's what we've done here. R sine of phi is basically times mv is going to give you the cross product. And remember, that's the same as mv times the lever arm, as we saw in the previous diagram. So we can finagle this to come up with a couple other equations. So, for example, if you consider all of the points, the sum of all the points in a rotating body as moving at 90-degree angles from a center. So if we're talking about a rigid body here, and we have all the points in something that's rotating from a center of mass, and we consider them to be moving at 90-degree angles from that center of mass, the sine of 90 is 1, and so it goes away. And then you'll remember from an earlier part of this chapter that velocity in that kind of a situation, something rotating around a center of mass, is r omega, where omega is the angular velocity. R omega is the angular velocity. So I can substitute r omega for the v there, and then if it's moving around a center of mass, then I can consider the angle of momentum for everything to be in a perfect kind of circle. And so that's a sine of 90 is 1. So the sine of 90 goes away, and then r squared shows up. Well, you might remember from a previous chapter that mr squared, mass times the radius squared, is another name for I, or the moment of inertia. If I take that and substitute I for mr squared, then I have another formula for angular momentum. Angular momentum is the moment of inertia of a body times its angular velocity. Now, torque is, as we saw earlier, the instantaneous rate of change of angular momentum per time. And so, if I then take the derivative of I omega, then I have I, which is a constant, times d omega dt, and the instantaneous rate of change of angular velocity is angular acceleration. And so I'm left with torque equals I times acceleration, which should look very similar to Newton's second law, which is force equals ma. So torque equals Ia, where the moment of inertia I is analogous to the mass. So the bottom line of this video is, although some of the formulas can be a little bit complicated, angular momentum is very analogous to linear momentum. And so we remember from the very beginning that P equals mv, so linear momentum equals P, momentum in a cross product with the radius from whatever point of origin you're looking at. And similarly, just like the sum of all the forces is the instantaneous rate of change of linear momentum per time, so the sum of all the torques is the instantaneous rate of change for all the angular momentums per time. And then finally, on the final slide, we had a couple other relationships, that angular momentum is equal to the moment of inertia times the angular velocity. This is for rigid bodies now, moving around a center of mass. And similarly, the torque for a rigid body moving around a center of mass is equal to the moment of inertia times the angular acceleration. So here you have it, angular momentum and the conservation of angular momentum.